Hello, welcome to Module 19 on vectors, matrices, broadcasting, and linear operations. So at this point, I can assume that you've used Jupyter and Python for some basic data analysis. I know that because we've gone through a lot of this already. I can assume that you can load and inspect data with pandas, and you can also convert data to NumPy. We've seen that in a few Jupyter notebooks we've provided previously. We have seen some simple train test splits, and we're vaguely aware of some baseline models, some super simple models. Even predicting the mean of some quantity is in some sense a model of that quantity, right? So we have all this data and we've modeled it at least just with regards to the mean value. We're not going to lean too much into formal linear algebra today, although linear algebra is sort of implicit. And we won't work with eigenvalues or matrix calculus or anything relatively fancy like that. We're just taking our time. We will treat NumPy arrays as vectors, matrices with shapes, and you'll see what that means today. By the end of today, you should be able to represent a real situation as a vector with units, use dot products to compute a score and explain it as a projection. We'll talk about dot products today. You'll be able to use a matrix to score many examples at once. So we've been talking about data points as if they're rows in a table. We've actually been doing a lot of operations already that apply one function to all elements at once, but we'll make this explicit with something called vectorization. You'll be able to predict and prevent broadcasting bugs by reasoning about the shape of your data. And you'll be able to communicate a claim with a baseline, a metric, and some kind of scientific test. So our example today is going to be admissions, like students applying to a university or a school, and we're going to treat it as a geometrical problem. So the university committee wants a transparent first pass scoring rule for applicants, something that can triage applications. The decision makers are going to be the admissions committee, so human beings at this point. What are they going to decide? Well, they're going to decide, out of all of the applications we have, who are we going to prioritize for review, for human review? But there's going to be many applications, and maybe we can use data science to kind of filter a little bit. So why do we need data science? In order to have a rule, like a set of rules, applied consistently and repeatably, based on real evidence, real statistical, real-world evidence. We're going to use data science for that. Let me just get in here. There we go. So we're going to have errors, right? So if we're going to have a system that's going to triage applications, and it's going to decide sometimes to pass a student on for a future review by humans, and then therefore maybe get accepted into the university, versus they're filtered, they're triaged, and they're never seen again, right? Those are two kinds of errors can come out of it. Once again, false negatives or false positives. A false negative would be one where we say the student should never be admitted, we should never even look at them on the committee, and you should triage them. So the model says they're a negative case, but that was false. That's a false negative, that's wrong. And that means, that's an example, for example, you could miss a strong student. It's a really good student, but the model triaged them because the model falsely thought that they were a negative case. We don't want that to happen. We want strong students to apply, and not only apply, but get admitted and make it past this filter. On the other hand, if the model is too permissive and is just sort of like letting everyone through and filtering nobody, then a lot more applications are going to have to go through the committee to be evaluated. It's possible that some students who appear to the model to be positive are actually not as strong as the model might expect. That's a false positive. So now we have to put all this energy and resources into analyzing applications that should have been triaged, and that wastes time and therefore other resources as well. So in this case, we're going to have a couple of measurements for the applications. We're going to have a GPA on a scale of 0 to 4. We're going to have the test score. Maybe they had to write a test before they applied, and it's scored from 0 to 100. And then there's a count of extracurriculars on their CV. It's always a good idea to do things. I'm happy to talk about this in class, actually, about what makes a good application. But I'll just mention previously that I know lots of professors who, some of them really care about your grades, but at least a few of them say they'd rather have someone with like a B plus average, but who nevertheless exhibits a lot of passion through extracurriculars, relevant extracurriculars, than having someone who's all A pluses but never does anything else apart from doing their coursework. Right? So the former looks like they care, the latter looks like they only care about grades. Anyway, that's a bit of a side note. These are three elements that typically matter to an admissions committee. So we're going to have another fictional data set and keep the units explicit. In a previous module, we talked about scaling, and we said we wanted to get rid of the scale, and because we don't want to overemphasize something like salary, when like a income to debt ratio might be more important, but that ratio might be on a small scale, and then therefore it would be totally eclipsed or shadowed by this massively scaled thing. So we scaled everything down to have similar scales. Now we're kind of doing something that might seem a little bit different, but it's not really. Now we're saying, well, we actually care about these different variables to different extents. A committee might have met and decided that GPA actually is what we care about the most, and test scores matter to some extent, but some people don't test well, so it doesn't matter as much as GPA. And extracurriculars, a lot of them are just kind of overinflated. They don't mean as much. They're just counts. So we want to measure these less. So if we wanted to make a model to predict who should be potentially let in versus who should be triaged out, we now have a weighting between these three variables. These variables mean more or less than each other. So that's the first idea, is the weighted idea. We want to have a score that's a weighted combination of these things somehow. We've kind of touched on this before, but really our data can be represented as vectors, right? A vector is just an ordered list of numbers that will represent one thing with multiple measurements. So a particular data point X, this could be an application X, is represented by the GPA of the applicant, the test score of the applicant, and the number of extracurriculars they have. And all of this is going to be in a list, an ordered list here, an ordered list of numbers. This constitutes a vector with dimension 3. A dot product, this is the main thing we're going to learn today. A dot product is a way to combine two vectors to get a single number. And this number is going to tell us basically how much the vectors point in the same direction. Another way of thinking about it is if you have two vectors, x, like the one we showed here, and w for weighting, how well is x aligned in the direction w? So let's scaffold our conceptions a little bit. This is a bit of a severe claim, but I think I can make this reasonably. All of modern data science is about structured combination of numbers. It's all about the numbers. Vectors are a single measurement. They're one-dimensional in some sense, but they have multiple measures. Matrices are collections of measurements. This can be like rows of data over columns of measurements. And linear ops is the procedures, the functions, the methods we have of mixing them or combining them in linear ways, which we'll define as we go. So here's some code that really doesn't do anything more than just draw this image. This image here draws a vector, and this is one way of looking at it one way of looking at it is just the way we've drawn here. The vector v has two dimensions, and the values of v are 3 and 2, right? So it's just like a list of numbers. But those lists of numbers can be represented in space, and it's going to help a lot for us to think of vectors as points in space. And we've already seen the idea of data as points in space quite a bit already. Okay, so the vector 3, 2 can be represented as this point over here. The first feature 1, has value 3, right? So there it is, 3. The second feature 2, has value 2. So that defines how high it is on the y-axis, I guess you could call it. And the vector is more or less just the arrow that points from the origin, 0, 0, to that point, right? It goes 3 over and then goes 2 up. This vector is represented as these two numbers, 3, 2. Okay, that's really all it is. I think it helps sometimes to be able to go back and forth between these conceptions quickly. So here's some more code that basically just represents a few vectors. So here we have an array. It has 3 elements by 4 measurements, and we're going to basically just draw these as a feature set here, right? So we have the rows are our observations, and the columns are our features, and the colors are just the values of those features. So this first observation is like one data point, and its features are 2, 0, 1, 3. The second row is a second data point. Its values are 1, 2, 0, 1, and so on. Okay, this is a much less common way of looking at a matrix in terms of this sort of heat map here, but it's just sort of exemplifying the idea that this data set consists of 3 observations, and those are the rows, and then the variables are the columns. You know, here there was only 2 dimensions, so we could easily draw this point in 2-dimensional space. Now every data point is represented by 4 columns, which are features, which are variables. It's really hard for human brains to conceive of data points in 4 dimensions, but you can think of each of these rows as a point in 4-dimensional space. Almost every data set you're going to analyze, even images, videos, text embeddings, survey responses, all of these will be converted in some sense into a matrix of rows and columns in this way. So norms. This is just going back into defining the idea a little bit. If the math might be, hopefully it's not too complicated for you, but we're just trying to get the high-level conception of what we're trying to define here. A norm is just a way to measure how large or long a vector is. So vectors, if their root is at the origin, can be described as like their angle, but also at how long they are away. You can have a vector or an arrow with a particular angle, but it can be very short or it can be very long, and that tells you where the arrow ends. Okay, so how long is that vector, regardless of its orientation in space? Well, that's what a norm gives us. There's a couple of different kinds of norms. All norms should be defined in terms of these 2 bars. So like 2 bars x 2 bars. This is one number, and this is a measure of how long the vector is. Okay, in general, it's defined this way. Okay, in d-dimensional space, the p norm is going to be the sum over all of the absolute values of every element in your row, raised to the power of p. Okay, so if you have a 3-dimensional vector, it's the first one, absolute value, raised to the power of p, plus the absolute value of the second one, raised to the value of p, plus the third one, raised to the value of p. So we've let me move this in again. We've did a sum over these values raised to powers, and then we, in some sense, kind of undo what we did by taking 1 to the minus p at the other side. This, I mean, for those of you who might be wondering now, is like, well, doesn't this p and this 1 to the power of p just cancel out? Well, not exactly, because here, like 1 to the power of p is applied over a sum, and not to the individual elements of that sum. Okay, so it's not like a product. If this was a product, then the p and the 1p would, in some sense, cancel out. But this is a sum, so that's not the case. So it's not exactly undoing what we're doing with these raising to the power of p's, but that's fundamentally it. Okay, this is the general form, and the value of p is something we decide ourselves. This is quite rare. Much more common, I mean, here's the common ones: the Euclidean norm, or the order 2 norm, and the Manhattan norm, or the order 1 norm. The Euclidean norm is basically the norm we always see when we're defining the length of something. You could have like a d-dimensional vector, right? A vector not in just 2 dimensions, but in those 4 dimensions we saw earlier. How long is a vector in those 2 dimensions? Well, it's defined in the same way, more or less, as if it was in 2 or 3 or 4 dimensions. It's just that we have to add more variables. So it's literally just the square root of the sum of squares. If I have like a 5-dimensional vector, d is equal to 5, and I'll just sum over the squares of all of the elements in my vector, and after I've done that sum, I'll take the square root. Okay, you might remember from like high school that that's what you get when you try to compute the length of the hypotenuse coming off of a triangle. It's going to be the square of the base plus the square of the height. That's going to be the square of the hypotenuse. So getting the hypotenuse, you just take the square root of it. All right, this is basically Pythagoras' theorem, is what the Euclidean norm is over here. Okay, so this should be very familiar to you. The Manhattan norm is just a simpler version of it. We're not going to raise anything to the power. I mean, we will. We'll raise it to the power of 1. So it's just the absolute value of 1 of the first dimension plus the absolute value of the second plus the absolute value of the third. This is called the Manhattan norm because Manhattan, it's a city in the country to the south of Canada. And the Manhattan has a very famous grid pattern in terms of its streets. So you're either going east to west or you're going north to south. And in order to get from one point to another, you have to go a certain number of units, say east, and then a certain number of units north. So the distance traveled between those 2 points will not be a straight line, which is going to take you through a bunch of buildings, and it's impossible, basically. But instead, it's the length you have to travel in one dimension and then the other dimension. Okay, so it's just the sum of those absolute values. The max norm is like literally as big as you can possibly be. That's when we set p to be equal to infinity. This is more just for curiosity's sake. I'm not going to, this is very kind of esoteric. I'm not going to ask you about this in the future. But the max norm is basically just the maximum value of all of the absolute values you have in your vector that represents the data point. From, so the max value between I going from 1 to d, which is basically all your indices. What is the absolute biggest value? That is your max norm. There's a proof for this, but we don't need to get into it. So in this course, when we write just a norm like this with no subscript p or 2 or 1 or infinity, by default, it's the Euclidean norm, because that's normally what we mean when we talk about like a vector in space. So again, we're thinking of the particular application as like, well, we want to filter applications to our university. So we want to basically ask the fuzzy question, how good a fit is this applicant? Which is like a fuzzy, messy way of thinking about our task. But we want to convert it into numbers, and we want to convert it into like repeatable data science. We want to convert that, how good a fit is this applicant, into a single number that we can use for decisions. So remember, every applicant we have is a feature vector with 3 values, GPA, test, and extracurriculars. And now imagine that we had a weighting before. We said that GPA was most important, test scores are somewhat less important, and so on. So the weighting, like how much the committee cares about these different things, can also be represented by a weight vector, right? So we have some weight. This is a number. Maybe 0.8 is our weighting for GPA, 0.15 is our weighting for test scores, and 0.05 is our weighting for extracurricular count. So we want a score to basically be a function. Here we call it the function score. It takes a single variable x. It actually takes 2 variables. It takes 3. It takes their x, but we assume that we know what the weighting is, and we assume we know what the offset is. Like b is like a bias term, an intercept, which you get for free. Like the points you get for free when you apply it to our university. So like x times w somehow, or x weighted by the weight vector w somehow, plus some bonus scores will give us a score of the applicant x. Okay, b is constant for all applications, and the weighting will be the same for all applications. So this is called a dot product. Like it's a little dot and it's a product. It's kind of like x times w. We'll define this in a moment, but we're going to want this to do a couple of things at once. The first thing we want is just to combine the features we have with the weights into one score. So we want to combine the actual GPA with a weighting for the GPA, and the actual test with a weighting for test, and so on. Okay, so we want to do that so we can get a single score, but also we want to measure how much, to some extent, the application X agrees with or points in the same direction as W. Okay, if an applicant has like really good extracurriculars but really horrible GPA scores for something, that representation, that X, will point in a different direction than the weighting scores, in the weight. Okay, so it's not only a measure of, it's not basically something functional that's going to get a score out of it, but it's also going to basically let us compare vectors X and W together. So I want you to play around with this. This is a, we can kind of play around with this tool down here. We're going to start with a unit vector in 2 dimensions. A unit vector is just a vector of length 1. So here's our vector down here in green. Okay, so X will be something fit along the horizontal axis. So, X is something we can move back and forth, left and right. And the length of the vector will be 1, or in other words, its norm will be 1. So here at the bottom, you can move this slider, and you can move this, this vector y back and forth. So this blue vector x is our reference. It's always going to be equal to the vector 1, 0, because it's 1, 0. But then I can kind of slide this other vector around. Okay, so I'm just going to move it around. So the vector is always going to be rooted at 0, 0, but I can change its angle theta, which I have down here. Okay, so play around with this yourself. You can kind of slide it back and forth, and this gives you, like I'm moving the y vector. So y is another vector. How much do they agree with each other? Let's think about that for a little bit. Okay, so on the right over here, I have this purple dot, which is basically moving up and down as I'm changing the degrees. Okay, so as I'm sliding the slider back and forth, I'm changing the degrees on this right graph. So here I am at 100 degrees. Here I am at around 50 degrees. So you can see how they correspond with one another. The degrees, again, the angle, is the difference between my red and my blue vectors, my y and my x vectors over here. So hopefully you can see all that. So the theta is sort of the angle between these vectors here. One thing I've drawn is this purple line over here, this projection. It's kind of like a shadow. So imagine like the sun is high above, and it's projecting a shadow, or it's shining down towards my vector x, and vector y, being between this source of light and x, is going to cast a shadow on x, and that shadow is shown here in green. That shadow is basically just the the value of x that I have in my y vector. So all I'm doing is I'm changing theta of this unit vector. It's basically rotating it around, but the value of x of that vector is in green, and hopefully you remember this. The value of x is the cosine of theta. Okay, so remember the cosine, like theta, cosine of theta is basically measured as the adjacent of a triangle over the hypotenuse, right? So here, if this is the angle in the corner over here, the hypotenuse is this vector. We can imagine a triangle coming down straight down here, forming a right angle triangle. So for this right angle triangle, this green vector only, not the blue vector, but the green vector will be the adjacent side, and the red vector is the hypotenuse, and the relationship between the adjacent vector and the hypotenuse is the cosine, and I can get the value of x here by computing the cosine. When the vectors are totally in alignment, right, and the unit vector y is totally flat on the horizon, then the value of x is going to be 1. So the cosine of theta is 1 over here. If I rotate it over here to all the way to, well, let's say 45 degrees. So 45 degrees, the cosine of theta over here is 0.707 radians, which makes sense. Pi over 4. Now I keep on rotating. I now have the two vectors are orthogonal to one another. What is the value of x here, of my data point? Well, it's going to be 0 in x. And similarly, cosine of theta gives me 0. I mean, 6 to the power of 10 to the minus 7 is as close to 0 as Python can get at this moment. And then you can keep on going, right? So now we're kind of projecting in the negative dimension. So now we've rotated so much, and theta sort of covers everything from this blue vector all the way around to this red vector. The red vector still casts a shadow on the same dimension as my vector x, on the x sub 1 dimension. What is the value of this shadow in that x sub 1 dimension? I still get it from cosine of theta. Now it's negative. So now it's about minus 0.5735. So you can see, and then I keep on going all the way to the end. this is as furthest away I can possibly get. So if I have one vector which is x, which is pointing just straight along the x sub 1 dimension, it has value 1 sub 0. I have another vector y, which is pointing in the completely opposite direction. This is like similar in terms of its direction. It's just the complete opposite. And because it's the complete opposite, the minimum score I can possibly get is -1. The y vector is like pointing as far away from x as it possibly can. So this is kind of a measure of similarity now, right? So if the vectors are identical to one another, the cosine of theta is equal to 1. They're maximally similar to each other. If they point in opposite directions, then the cosine of theta, the cosine here of 180 degrees or pi radians, is going to be -1. And if the vectors are orthogonal to each other, so if there's like a 90 degrees between them, or pi over 2 radians between them, then like they're saying different things. They have nothing to do with each other. There's no shadow. There's no relationship between x and y. They're totally different. So the relationship is 0. There's nothing there. So again, here's just what I said before. If theta is 0 or close to 0, the vectors point in the same direction. Cosine of theta is 1. That's like the full length. The projection is maximum. The similarity is maximum. If they're perpendicular to each other, which is orthogonal, means the same thing. Cosine of theta is 0. There's no projection. There's no shadow. And these two dimensions are kind of like just not even saying the same thing. If you remember a few modules ago, we used one-hot encodings to change like the different types of values of cities and employment status into different points on different dimensions. And that just basically just says these are totally like not comparable to each other. And then if it's totally the other way, then vectors point in opposite directions. They kind of, in some sense, are similar in terms of their direction. They're just totally flipped. So their difference is maximum. It's -1, which you get from cosine of theta. So far, the dot product, remember the measure we want to have is sort of how similar the two vectors are. Here we're calling them x and y. On a previous slide, they were x and w. X dot y is now just cosine of theta. This tells us how similar these two things are, how much they point in the same direction. Okay, so for unit vectors anyway, x dot y will be somewhere between -1 and 1. Okay, but this is not really the most. This is not the most standard situation. Like GPAs go up to 4. Number of extracurriculars can be a number between 0 and a dozen or so. So like the actual norms for our applicant data X will not be unit vectors like this. We're just getting started. We're just kind of understanding that the angle between two vectors can be used as a means of talking about how similar those vectors are to one another. I want you to just play around with this until the idea becomes sort of intuitive to you. Look at the angle between the red and the blue vectors. Look at how changing it changes the cosine of it, and how the cosine basically tells you how similar these are to each other. And the similarity is represented by this projection, this shadow, which I represent here in green. Okay, the shadow goes from being 100% to 1 to minus 1. So that's sort of like the conceptual scaffold. Now we have to go a bit deeper in order to really understand how things work. The projection of y onto x, we called the shadow a few times. This is basically the like how much y extends in the direction of x. Okay, so we saw this a moment ago. When the norms of x and y are both 1, then the length of the shadow is just cosine of theta. We understand that. But what happens when the length of, say, y is not equal to 1? So we're going to use these sliders now. We're going to change the length of y and also the angle. So here you can change the length of x. See? I'll set it back to 1 again. Here I can change the length of y. So remember, like in real life, the units will be all kinds of different numbers. I can't guarantee that like my norm will always be exactly 1. So let's make it like a bit bigger here. Actually, I'm going to make it smaller to start with. So for some reason, I'm dealing with units which are very small. And my length of y is now something like 0.8. And I can still change the angle like I did before. So like I kind of mentioned this earlier, but you can kind of see that the shadow, which now is a green dashed line, which I get, which is the x component of this this orange vector, basically will form this right angle triangle, in which the vector I care about, which is y here, is the hypotenuse of this right angle triangle, and the adjacent side is the x component of the projection, and then the final one is just the height. Okay, so again, a vector in the two dimensions are just defined by x and y, so this should make intuitive sense to you. So I can still make these changes here. As before, when the two vectors are orthogonal, when x and y are orthogonal to each other, in some sense it doesn't matter what the length of y is. I can make it very small, I can make it very big, but y and x kind of are in totally different dimensions. They're describing different phenomena. So as you can see over here in the corner, the dot product of these is going to be equal to 0 all the time. But there's going to be some other changes. So imagine I make y really small and I make x, say 45 degrees. There we go. So now, if I change the value of the length of vector y, its projection onto x will change, obviously, right? So that this triangle is getting bigger and smaller, so the length of the adjacent side, the x component, will get smaller down here and get bigger over here. And similarly, the values of my dot product, which I'll redefine in a moment, should get smaller and bigger, because in this sense, down here, the vector y is really tiny, and I mean, technically it kind of points somewhat in the direction of the blue vector x, but not really, right? It's really, really small. If I make it bigger, then it more and more, it points in the direction of x. Its x component, indicated here as this dashed green line, is greater and greater, right? The agreement, I guess you could call it, of the orange vector y and the blue vector x increases as I increase the length, keeping the theta constant. So for these right angle triangles here, remember cosine theta is adjacent over hypotenuse. So the adjacent side is the shadow. And the shadow can extend here beyond the actual extent of x, or it could be smaller than x. I don't really care at this point. I'm just talking about the extent of the vector. And the hypotenuse is still the length of y, which is the norm of y. So the projection length, so the amount of agreement when x is 1, so I've kept x being 1 over here, is now going to be multiplied by our norm y. Okay, this describes what I was just playing around with a moment ago. If y is let's say start off with 0, so 1. So here the length of y is 1, and my dot product is 0.707. If I double the size of y, then I double the size of the dot product. It goes from 0.707 to 1.414. Okay. So far, so good. And this is kind of what I expect. So, and this I get from the shadow, right? So before the shadows were constrained by the unit vectors. Now y is no longer constrained by the unit vector. But I still care about the shadow, the length of this green dashed line, and I can get that simply from the Pythagoras, cosine, just like SOHCAHTOA says, is adjacent over hypotenuse. So now, I have a somewhat more general form. X dot y equals cos theta was fine when y had length 1, but you can see I get x dot y equals cos theta when this norm is 1. But if the norm of y is not 1, then my overall dot product gets bigger or smaller respectively. But x can also vary, right? So the value x over here can also change. X here, it's a unit vector, but maybe x doesn't in some sense believe in itself as much, so the extent of its vector in the x dimension is small, or it could be very adamant about its dimension and go here all the way to 2. So I can change the weights in this case, of my x vector, and that's also going to have an effect on that should have an effect on the extent to which the orange vector y and the blue vector x agree with each other. We're just going to basically scale here. So there's a proof associated with this, which we can not necessarily have to get into. But here we have the shadow of y along x, which we computed a moment ago, and we get from this representation here of cosine. But if we make x bigger, then this agreement counts for more. If we make x smaller, then the agreement counts for less. So we just scale by the norm of x, by the length of x. And this is our final representation of the most general form of the dot product, x dot y. Right? It's the norm of x times the norm of y times the cosine of the angle between them. And we're done. We've been dealing in 2 dimensions because, it's easy to go back to our high school math and remember what to do with cosines. And how to zoom out. But these vectors can be in arbitrarily many dimensions. Remember way back when we had vectors with 4 dimensions, which are very hard to conceive of? Human brains can still think in 3 dimensions, so we're going to quickly take a peek there. In 3 dimensions, nothing changes conceptually. Like vectors are still arrows in space. It's just that we have 3 numbers instead of 2 numbers that represent them. There's still an angle between them. You can still take 2 vectors and measure the angle between them. And the same rule holds. Like all of the logic that we just walked through will hold in an arbitrary number of dimensions, including 3 dimensions. So the dot product is still the length of x times the length of y times the cosine of the angle between them. So here's a plot in 3 dimensions. It'll keep x fixed. The red vector is going to be fixed, and it's going to rotate y in a plane that contains x. So we can see sort of the angle between them. So here as I'm moving x, the angle is 0, and I can kind of move x around. Sorry, I can move vector y around. So the vector is changing. You can rotate this yourself. Again, always it makes more sense if you just play with it yourself. But I'm basically rotating x. So right now they're basically overlapping in that dimension, but now I can move things around. This purple line is sort of the shadow we were talking about before. So x is sort of like a dimension. Right now it's not perfectly flat, on one of our planes. It's kind of pointing up a little bit. But if we just extend, that basically is a dimension in space. And we can instead of treating it as a Euclidean dimension like x, y, and z, we can imagine that this vector x is its own dimension in space. And we can rotate y around that dimension. And then when we rotate y around the dimension, it'll also cast a shadow on the dimension described by vector x. That shadow is here now drawn in purple. But everything that we've mentioned earlier before, like the projection of the turquoise vector y onto the red vector x, is shown here in purple. That's a projection, that's a shadow, and it's still going to be described as in terms of the cosine of theta. Okay, just like before. It's just nothing's really changed. We've just went to 3 dimensions, and we've moved x off of the horizontal axis a little bit, but everything else is exactly the same. That's all we need to know. So right in this graph, you can't really change the extents of x and y, but I've already kind of defined them already. So x is its norm is 1.58, and the norm of y is 1.3. The overall dot product, which is not shown here, you can compute it yourself. You can say, well, if the angle theta is 150 degrees and the lengths of these vectors are, as I said a moment ago, then I'm giving you the cosine. What is the dot product? How similar are vectors x and y to each other? So we have like a visual geometry. We've pictured vectors moving in space. Any 2 vectors that are rooted together, as they rotate away from each other, will have a degree of an angle between them, theta. Each of these vectors will have a length, which we have as norms. And all of that gives us this geometric rule, which we've described in terms of shadows and cosines and length and so on. So this is really important. I put a box around it before, but you might want to just write this out a few times. Okay. Our geometric rule is in terms of angle and length, but we're just doing practical data science. So I mean, that was all practical. We need to understand like what is actually going on in the world, in the geometry. Let's see if I can just move this around a little bit. There you go. But fundamentally, we're also going to be dealing with code, and we want to just deal with these rows of numbers in a programmatic fashion. Okay, so we're going to deal with them in terms of coordinates. Remember, we define vectors in terms of like x and y and so on, these points in space. So let's go ahead and break things down a little bit. We have now just written out one vector can be defined as x sub 1, x sub 2. That's like the amount it extends in one dimension, the amount it extends in the other. And y will have two other values. We'll call them y sub 1 and y sub 2. And that's the extent of the dimension y in the first and second dimension. Their lengths come from Pythagoras. Like this is the exact formula we saw a moment ago for the 2 norm. But you know, we talked about this, right? So the length of the hypotenuse, which is the vector itself, is going to be the square root of the sum of the squares of each of those sides. Okay? Let's zoom out again. So we know this. Okay? So the length of x is defined as it normally comes from Pythagoras. The length of y comes from Pythagoras, and it's fine. The distance between these points. So if we take the vector x and the vector y and subtract them one from the other, that will give you another vector. And how long is that vector? So the difference between vectors is just, you take every dimension one at a time and take, in this case, the square difference. So x extends a little bit in the first dimension, y a little bit in the first dimension. How much do those two quantities differ? That's just x sub 1 minus y sub 1. Now in the second dimension, x has a value, y has a value. How much do those vectors differ? It's just the difference between these. We square it because we're dealing with a 2 norm. We take the square root, and that'll tell us basically the length of the vector that connects the difference between x and y. So the same distance can be related to the angle at the origin. So x minus y, the norm, is equal to the norm of x plus the norm of the second minus 2 of our dot product. This is just the cosine rule for triangles. I should mention for a moment, I mean, this should be something you've already seen previously in high school, but this is a bit of just digging into the details a little bit so we can understand like that what we obtained geometrically is true on paper also. Okay, so I'm just measuring vectors, I'm measuring distances between vectors, I'm rewriting this distance in terms of x and y and their difference. So this is a cosine rule for triangles. You might not actually remember this rule, but for the time being, you can believe me that this is by definition. Now, if you expand both sides in coordinates and match these terms, then and you actually kind of write out, so you write out like this line 2, and you replace the left-hand side of line 3 with this square root. Then you move things around, you expand the norms also, like we defined a few slides ago. Then this mystery quantity, this x norm times y norm times cosine of theta, will just be x1 times y1 plus x2 times y2. Okay, and that's it. So this is really more in terms of on paper or in code, how we might represent the dot product. I think it's easy to conceive of the dot product in terms of vectors in space and angles between them. But normally we're not going to look at vectors in our code visually. We're going to just write everything down in code. Numerically, we want the score at the end of the day. How do we compute that score? Well, this is how we compute the score. Everything we talked about previously can boil down into this one line over here. The dot product of x and y is just the product of the values in the first dimension plus the product of the values in the second dimension, plus however many factors you need for all of the different dimensions you have. So in general, the dot product of x and y, or x and y are d-dimensional vectors, is just a sum over the products of each of the pairs for those dimensions. Simple. So we can see this example just written out one more time. We have two d-dimensional vectors. X is x sub 1, x sub 2, da 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 da, x sub d. W, right, so the weight vector, is w sub 1, w sub 2, da 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 da, w sub d. In our admissions example, we had 3 dimensions, so d was equal to 3, but this generalizes to any number of dimensions you can have. So the dot product we just defined is the sum over all of the dimensions of the product of one vector for that dimension times the other vector dimension, value for that dimension. So it's w sub 1 times x sub 1 plus w sub 2 times x sub 2 plus all the way to the final added sum, which is the product of w sub d times x sub d. And this is, we're done. This is by definition. You'll notice that for each of these terms, you can swap x and w around. So you can like w sub 1 times x sub 1, because these are just numbers, is the same as x sub 1 times w sub 1. And then you could swap x sub 2 and w sub 2 all the way down to x sub d times w sub d. The overall result will be nothing. Like we haven't really done anything. You can do this with numbers. But by definition also, if we've done this, then this sum of products will be equal to x dot w. So in other words, w dot x is equal to x dot w. And that means that the ordering of w and x doesn't matter. Okay. This is good. This is similar to what we'd expect in regular old multiplication. It's going to be the case that sometimes multiplying matrices together, the order in which you do it does matter, and you can't just swap around variables in this way, but at least for dot products, we're good. W dot x equals x dot w. So we want to do data science. We have our geometric ideas. We've converted that to something on paper in terms of like a mathematical representation, which, because math and code is the same thing, we can imagine how to produce that sum. You can do a for loop for every dimension, for example, and then just keep accumulating and adding together the products between the values for the dimension you're currently in. So we haven't really done a full projection yet, though. This is the actual vector object that's produced by projecting a vector on another. Okay, so we've computed sort of the extent of agreement between the two values. X dot y more or less tells you the extent to which x points to y, but we didn't actually get the vector itself. So maybe we'd actually want the vector to come out, so we could do some downstream processing and describe our applicants in a space defined by our weight vector w. So this can be helpful. The similarity of data points, a cosine similarity between feature vectors is going to be based on the dot product. So the dot product will tell us how similar two vectors are. This could be also two applicants. So we've been talking about x and w. X is a data point, w is a weighting scheme. But we can have two applicants, call it a and b. These are two different vectors. How similar are these two vectors to each other? That is just the angle between them, essentially, assuming that the units, that the scales are the same. We're going to see linear regression at some point. A linear regression is basically just like the best fit line on a data that describes data. So picture a scatter plot like you might see in a spreadsheet application, all these dots. A linear regression fits a straight line through those dots. Okay, this best fit line is literally a projection on some target space spanned by all the features. This will make more sense when we get into machine learning later in this class. But when we're doing linear regression, which is like it's a gateway into machine learning, we're going to be dealing with projections of the type we like to do now. And also later we're going to talk about dimensionality reduction. So, using three variables to define our applicants is simple for us. But in a lot of real world situations, you might have hundreds, maybe even thousands of measurements that we're dealing with. And that's way too many for our squishy human brains to contend with. So we want to reduce the dimensionality down to some other smaller representation of data. And then how do you do that? Well, the relationship between points, how similar they are to each other, is going to be very important, and we're going to get that similarity from this geometry. Like the difference between 2 points is the difference between 2 vectors, and we know how to do that now. Just wrapping up this idea quickly, okay? So this is the important thing to remember right now. A dot product remembers how much one vector acts in the direction of the other, and it'll give you one number, one value. There's other kinds of ways you can multiply vectors together that will give you either other vectors or maybe other quantities, other data types, and you can get those confused. So later on, we're probably going to encounter cross products, and that's we're gonna deal with it later, but that's not going to give you single numbers of output. Because we haven't even seen that yet, it's too early to describe how they're different. But and then mnemonic to remember which is which. But I like the dot product is like a single point, therefore it's like a single value. A dot product gives you a single number. That's hopefully something you'll be able to remember. A dot product is also symmetric. So it's a symmetric measure between two vectors. It'll be scaled by lengths, and cosine theta will tell us like the fraction to which they agree with each other, right? So there's 3 components to it. The first 2 are basically the lengths of the 2 vectors, and the third component, cosine theta, is just the degree to which they point in the same direction. So let's make this more concrete and go back to our admissions as geometry. So here's a particular example. We have a GPA for an applicant of 3.2. I think all of you can do better than that. So, but anyways, this applicant has 3.2. Their test score is 80, and they've done 2 extracurriculars. Maybe they've done a research project with a professor. That's one, and they've led community outreach, which is another, whatever the case may be. The admissions committee says, well, GPA is the most important. We'll give that a weighting of 18 on some scale. The test score is actually, in this case, they've weighted things a bit differently. Now, like they say, the test score is almost not important at all, because people can test poorly, or maybe there's a problem with the test, so the test score is now weighted 0.6. And extracurriculars are weighted 2.5. So not as important as GPA, but more important than test scores. And then we have B. B is our like little bonus, or intercept, or bias. They all mean the same thing. That gives us like the total number of bonus points our applicants get. It's not going to change your ranking. Like if you have data points and you just kind of raise all of them or lower them by a certain amount, the ranking is going to be the same. But if you care about the actual score, and if the actual score is going to help you throw applicants away or keep them in your pool, then the bias will matter here. In this case, everyone gets a -20. So this is a pretty strict university. So we know how to do dot products now, right? A dot product, you can think of it geometrically, but we've also converted that geometry into, on paper, how to actually just go about computing the number. And the computation is just the sum over all of our dimensions. It's the value in the first dimension of one vector times the corresponding value in that dimension for the other vector. Okay, so the first dimension here is 1. It's 18 times 3.2. That's the first dimension, plus the second dimension, 0.6 times 80, plus the third dimension, 2.5 times 2. You can write this out yourself. This all goes to 110.6. And we're going to be adding this kind of bonus or bias, which is -20. So 110.6 minus 20, the overall score is 90.6. So this particular applicant, according to our uniform constant weighting scheme and our uniform constant bias, is going to be 90.6. So now we can easily do this for every application. So the weights being the same, so keeping 18, 0.6, 2.5 constant, I can swap in what's inside of these parentheses. So 3.2 is whatever the next applicant's GPA is. I replace 80 with whatever their other applicant's test score is, and so on. I get another score at the end of it, and now I know, I can compare these two applicants, in terms of how much they agree with my weighting. And I can also compare it to some baseline. So maybe after I compute the dot product for all of my possible applications X, then I can say what the average is of overall my scores. And if a particular person's application is above this average, then I can say they look good. We should consider them in our applicant pool, and we should dig deeper into their application. Or if they're below the average, then we'll say they're the bottom 50%. We can discard their application. So here's just a little kind of geometry view. Again, this is basically just a repeat of what we saw earlier. We have 2 vectors. We have the vector X representing the applicant, and a vector W representing how much we care about the different dimensions. Feature 1 and feature 2 here are just 2 toy units. Like this isn't exactly like the units that we talked about earlier. They're just toy units just so you can see this. These vectors are always rooted at 0, 0. Now, their lengths are going to be different based on how I set W, based on how well X is doing. But I can still project X down onto the direction defined by W. So you can imagine extending this vector W out like an arbitrarily long period so that I can project X onto it at a right angle. So shown down here somewhere is a right angle. And you can kind of tilt your head a little bit and you can see how this right angle has a hypotenuse, which is X, the adjacent angle, which is the projection, and then the angle between these two things is shown down here where my mouse is. So everything lines up pretty well, and it's nice when everything sort of fits together like this. So here's a little anti-example, this naive ordinal encoding. We talked about encoding dimensions numerically, and this is one maybe the first time we saw why this could be a problem. Like previously we had like the city that someone comes from is Halifax or Truro or Sydney, and we said, well, we could be crude about it and just replace Halifax with 0 and I don't know, Truro with 1 and so on. Now, I said that could cause problems, and then I just kind of left it, and then we did one hot encoding, and then I left that also. But now we're going to see why it's a problem. So imagine if we have overall extracurriculars, that's a count. Imagine we've binned them. So we've said, if they've done no extracurriculars, that's label none. If they've done 1, that's a label some, and if they've done 2 or more, that's label lots. Okay. So now we have, instead of just a count for extracurriculars, we just have these labels, none, some, and lots. So again, same problems we saw in an earlier module. This implies distances that might not be real. Is lots of extracurriculars actually twice 1? Is lots twice some somehow? That doesn't really seem to make sense to us, like linguistically, but also therefore meaningfully, semantically. So like now we have vectors, now we have to think, what is the arithmetic, does the adding and subtracting of these things actually make sense? So let's generate the admissions data set. Here we're doing some random generation. We're going to make 800 applications. We have a random seed. So we have from NumPy and from the random component of NumPy, we have like the default random number generator. And just to make sure that everything's repeatable, and every time I recompile my slides, I'll get the same numbers, we specify the seed, 1109 in this case. So I can sample. So this is getting a little bit too detailed. We're actually going to see normal distributions in a future module. This is just a Gaussian distribution. This is just saying I want a normal curve where the average GPA is 3, where the standard deviation is 0.5, and give me n of these data points sampled from this curve. Give me 800 data points sampled so that the average is 3 and so on. So that's where I get the curve. I want to clip. So if I'm sampling from a Gaussian curve like this, sometimes I might accidentally get very high numbers more than 4 or very small numbers less than 0. All I'm doing here is I'm saying using the NumPy function clip, clip anything less than 0, clip anything less than 4. Right? In other words, just like set things less than 0 to be 0, set things bigger to 4 to be equal to 4. I sample my test score the same way. Everything's exactly the same except the average is 70, the standard deviation is 12, the smallest value is 0, the biggest value is 100. And then I'm sampling from a Poisson distribution. I haven't defined this yet, so I'm going to define this a bit later, but this is just basically defining like the numbers of events that's occurring. So like on average, there'll be about 2 events, 2 extracurricular activities per person. Give me 100 of them. Don't give me anything less than 0 extracurriculars. Don't give me anything more than 100 extracurriculars. Sorry, more than 10 extracurriculars. So now we have our committee has decided our weight structure. This is the same one we saw a moment ago. We have GPA matters a lot, extracurriculars that matter a little bit, test scores matter somewhat. We have our bias, B, our bonus score, B. And then imagine there's some noise too. So again, this is something I have to keep on emphasizing. Whenever we measure something from the real world, sometimes what we're measuring might be errorful in some way. In some sense, you could imagine this being like if somebody did poorly on a test. on that particular day, that's a little bit of a noise. That doesn't represent their true ability in taking tests, but there's some noise associated with it. Regardless, I have 800 GPA scores, 800 test scores, 800 extracurriculars, and then the numbers for each of these things. And all I'm doing is stacking them together. NP allows me to stack their columns, so I'm just basically stacking them column by column. You can go ahead and maybe add a line between 15 and 16 here and just print out X to make sure that everything is what I say it is. Again, if I'm making mistakes at any point, you can bring it to my attention and get some team marks that way. And then finally, so we have this admission score. So admission score is going to be, what we mentioned a moment ago. It's going to be X times W. I'm going to define what this at thing means in a second, plus some noise. So like the measurements might be noisy, plus our bias. And then clip it. So like you can just say the score is going to be something between 0 and 100. Okay, so now I take all of this NumPy, like this matrix of numbers, and my admission scores I've computed, and then I'm going to combine them together into a data frame in which these columns have named column headings. So here are my heading titles as strings. Here are my values following the colons. All of this goes into a data frame, which I'm calling df for now. And then df.head will show it to me. And here it is. Here's only the first 5 rows, so the GPA that I randomly generated of the first applicant is 2.9. Their test score was 74. They've done 0 extracurriculars. This person doesn't look like they're... Actually, this person gets an admission score of 84.7 according to our weighting scheme. Maybe a different weighting scheme would have given us a very different admission score. In fact, go ahead, go into this code, and fiddle with the weight scores over here to see what happens when you fiddle with them. But so far their application looks pretty good, despite their low GPA and their low test score. Moving on. So this code, so here it is. This is where I describe it. So we talked about dot products. In math, we have X dot with a big dot. Y is the the dot product between X and Y. But there's no big dot on your keyboard. So how do you represent that in Python? Well, in current versions of Python, implement these multiplications for vectors using this at symbol. So X at W true. It's not an email address. It's a dot product with vector X and the vector W sub true. And I just advise you to read more about it here. So here's a link. And as usual, if there's a link, click here. This will tell you a little bit about it, just for some background. Okay, but for the time being, just remember this at sign represents the dot product when given vectors in Python. So let's see a score of one applicant and show the contributions of their score. So let's consider the first applicant here. So here's, I care about the first index. So in my data frame, in the location described by IDX, index 0, pull out the GPA, the test score, the extracurriculars. And so this inner square brackets basically just gives me a list of the columns I care about. This outer square brackets basically tells me to pull the vector, give me that row from this data frame. And then here's the kind of the crucial thing which I think highlighted at the very beginning in the outcomes. To NumPy kind of undoes the pandas thing. So pandas has all these functions associated with it, which is deeply involved with data frames. But if all you want is just a matrix of numbers, just lists of numbers, essentially, NumPy is a lot simpler. So converting this data frame of this row to a single vector X, which is a list of numbers, you can do so by calling the toNumPy function. You can go ahead now and just recompute that you're getting the same numbers here. So np dot, as you might expect, implements the dot product between two vectors given as arguments to that function. And then you can add b underscore true, that's our bias we computed previously. This is our score. Now we can create a new data frame, consisting of GPA, test score, extracurriculars. These are the features. We'll have the X component, X will have GPA, test score, extracurriculars. Our weightings will have those components, and then we can compute the dot product. Confusingly now, I'm using a star. This is kind of the third operator we've seen for the same concept in math, and therefore the highest level of representation. A big black dot is how we define a dot product. A moment ago in Python, Python is just a code representation of math. We need a symbol for that. There's no big dot that we can easily get to, but we can easily get to @ so @ is the same function. NP dot in some way, I guess, is actually the third way we've represented the dot product. But now in text, sometimes you'll see the star here. So the star means times, and you, the reader, are supposed to know that when you see W star X, this means W times X. And so far, the only way we know how to multiply two vectors together is the dot product. So this means the dot product. But this can be confusing sometimes when you have multiple different ways you can multiply vectors together. And indeed, multiplying matrices together, there's many ways you can do that as well. So you have to always be very careful that you're communicating things in a way that there's no ambiguity. Regardless, I get my contributions. I'm doing a bit of extra lifting here. And I get my intercept. So I'm adding an intercept row here. And I'm saying well, the feature is called intercept. There's no intercept for X and W really, but there's an intercept for my dot product, which is my score, which is going to be B sub true. And then just print it out on line 12. So here's my new data frame I just constructed. Features versus X, W, and W sub X. Actually, so here it's literally just the components of it. So it's just so here, on the right side over here, I should have mentioned this, apologies. Before, when I was using the @ sign to multiply vectors, now this is just multiplying individual elements of that vector. So the number in the dimension 1 of W sub true times dimension 1's value in X. Okay, so that's where we get down here. 2.914914 times 18 should be 52.468452. And 0 times 2.5 is 0. Okay, so now you can kind of see this is because we're kind of exploding the dot product, and we're seeing to what extent each of the dimensions have an effect on our overall score. So you can see that extracurriculars for this particular applicant has no impact on our score. It's a 0. And then the GPA and the test score are roughly, they both contribute rough amounts. Even though the weight for the GPA was bigger than the weight for the test score, maybe, we were smart about it, and we realized that, the GPA is not scaled. So therefore, you need a weight factor that is scaled appropriately to account for the smaller scale of GPA. A test score is in a much bigger range, so maybe give it a smaller weight so that when combined, you'll get something on the same order of magnitude. But there we have it. You can just visualize this now. So I'm just, I'm making yet another graph. The Python code is not provided here, but you know how to make a graph now of this last column. So you can see the weighting of the GPA dimension, the weighting of the test dimension of extra and intercept. And you can kind of see this is where the overall score for this applicant came from, according to this weighting factor. The predicted score with no noise is 76.9. The overall observed admission score with the noise we've added previously was 84.8. A little bit different, but that's fine. Because the noise could have been nothing if we chose it to be, and we added no noise to the previous computation. So this is where we want to quickly do some vectorization. So rather than computing every single score row by row and doing a for loop, for every element of our matrix for every applicant and for every column of that applicant, start summing up the products, we can do everything at once very quickly. We can do one matrix multiplier once over the entire matrix and get us all of the x's times w in one shot. And this is going to be not only simple and elegant in terms of our code, which is always nicer. It's a lot less likely to have errors if you write small code. So keep the code nice and tight. But also, it turns out that doing vector operations, operations that can be parallelized over the multiple cores in your CPU or over a GPU, for example, is also going to be a lot more computationally efficient, a lot faster. So this is what we're going to be doing now. So we have our x's. We get all of our data frame data, and we convert all of the data frame into one big NumPy object, big X. Big X is now a big matrix with n rows. We have, say, 800 rows from our example, and d dimensions. We only have 3. W we'll call is W sub true. Its shape is d-dimensional, so W is a vector of 3 numbers, GPA, test score, extracurriculars. That's a d-dimensional vector. And then B true is just a number, a single number. Okay, so we want to obtain a new kind of representation of our data. We want to get scores, predictions, like a vector, for all of our entries. Here, the code X is only giving. Okay, yeah, I'm ahead of myself. So I have 800 elements in X. I have 3 elements in W. Now X at W will multiply each of the rows in X with the vector W. It'll multiply them as a dot product. So I'm going to get quickly and automatically the dot product for every single one of my rows of my data matrix X. And this behind the scenes will be handled for you potentially in an automated way. So you could compute that entire matrix simultaneously and distributed and in parallel, because computing the dot product for the first applicant should have no effect on computing the dot product for the 500th applicant. So this is getting a little bit in terms of the behind the scenes, but that's what's going on. From our point of view, all we're doing is doing a dot product on all of these rows at once. Instead of having to have a for loop, we can just do it with this one expression. We've saved a ton of time. And then, this is going to be a vector, because every dot product of W in each of our rows is going to be a single number. But we have 800 rows in X. We're going to have one number for every row. That's a vector of length n. There's n components to that vector. And then adding B to that vector, we'll just add the number B to every element one by one. Okay. I want you to look at this really and print up all of these values and make sure everything's working as it should. You can try to break things a little bit. So maybe try making W a vector of length 2, and then see what happens when you multiply X with W down here, where X has 3 columns and W only has length 2. What happens? Try to break it as much as possible. But regardless, the code works. And on line 6 here, I'm just writing out, the first 5 elements. So from the, y hat vec with these square brackets basically is indexing from the first element of this list to the 5th and writing it out to the screen. And here are those values. The first applicant gets a score of 76.9, the second one a score of 85.9, and so on. And everything looks good. And so now I'm kind of done the main data science work of our applications pool. And now I have scores for all of our applications. This is the loop baseline. This basically will do the same thing, but we'll do it using a for loop. So this is kind of the baseline. This is the worst version of what we just did. We'll start off with our y hat. This is our predictions. And then we're going to iterate over every row of x. X.shape0 just says this is the number of the dimension in the dimension I'm specifying. So dimension 0 is rows, dimension 1 is columns. So x.shape0 tells me the number of rows in variable x. For I in range of that number, we'll iterate from I being 0, and then 1, and then 2, and then 3, all the way up until this value. So it's basically going to iterate over each of these rows of my vector x. Over here, what's happening is I'm taking the ith row of x, which is the vector of 3 elements. I'm taking the dot product of it with my 3 element vector w. I'm adding my baseline, my bias. And then this is a number, this is the score of the applicant. I'm just going to append it to my list. So on the first iteration, initially y hat loop was empty. I've gone into my first iteration, I'm considering the first applicant. I've computed the score of the first applicant, it's a number. Append that number to this loop. Appending a number to an empty list will just create a list with 1 element, this new computed element. And I'm done my first iteration. Then I go to the second iteration of this loop. So now I is going to, before I was 0, now I is 1, take the next row of x, get the dot product of that next row of x with the vector w, add b to it. That gives us the overall score for this applicant. Now append their score to my list y hat loop. So in the previous iteration, I've had 1 number in this list. Now I'm just appending a second number. So I have 2 numbers in this list. You can see that if you iterate over all 800 rows of the variable x, that's the 0th dimension, and I've appended a number every single row to y hat loop, at the end, I should have a vector y hat loop 800 elements long. This is only a list, so I'm just making a list of numbers, but I can convert a list of numbers into something called an array, which NumPy just uses to represent lists essentially. And now I can just check whether or not this y hat vec, which I obtained from this vectorized, nice, elegant matrix multiplication. This is like the elegant way of computing dot products for every row. I can compare it against what I obtain with a loop, y hat loop. So y hat loop is doing dot products row by row, but it's doing it explicitly through this for loop. I can just compare them against one another, so I can subtract one from the other. So I have a vector and another vector. I just subtract, the first element from one from the first element of the other. That's my first entry. I can subtract the second element of the first vector from the second element of the second vector. That's the second entry, and so on. I'm computing the absolute value now, just to say, like, is there any big differences happening here? And find the biggest difference that I have. Like, what is the most I'm wrong when I'm doing things in a loop versus when I'm doing things in a vector? And then the result of all of this is essentially 0. So very rarely in Python and NumPy and in pandas are you going to get absolute zeros here. But 2.8 times 10 to the minus 14 is such a small number, it's about as close to 0 as you can get. And this more or less confirms the idea that computing the y hat, like the the dot products, row by, like, all at once, gives us basically the same number as doing so explicitly using this more complicated for loop. Okay, so the baseline approach works. There's no numerical difference than what we get using the matrix operation from before, but because it's more complicated, because I have a lot more things going on in this for loop, there might be bugs. Maybe my for loop is on a somewhat wrong range. Maybe I've done something on the wrong dimension. It hides the algebra to some extent, which is not good. You want to keep things as high level as possible. So this is just basically saying you can do things in 2 ways. You can do things carefully step by step, which is how we tend to do things in code when we're learning how to code, or you can do things elegantly in one foul swoop. We're not going to take, unless I'm specifically telling you that I'm wanting you to do vector operations in your assignments or in your Jupyter notebooks. Like, I don't really care about this difference at this point, but it's something to keep in mind for as you keep moving through your data science journeys. So we're almost finished. We're not quite done yet. Our baseline will give us sort of our baseline decision method so far has been the average, right? So we've taken some data, we call that the training data. We've computed all of our statistics on it. We took the average of all of our scores. And as I mentioned several slides ago, if an application is below the average, we throw them away. And if they're above the average, then we keep them for more analysis. That decision is our baseline, right? The mean score is our baseline. And it's a rule that we've come up with, but it's very, very simplistic, right? And so far, it's just basically using our dot product to get these values. Okay. We'd like to practice this habit. We've already kind of started this a little bit of not testing or doing evaluations on the same data that we used for tuning. So we got our average from one set of data. We might have gotten a linear rule from another. Where are we? I've split the data. So this is using a function called train test split. It comes from sklearn. It comes from a model selection section of the sklearn library. So all I'm doing here is saying, well, take all of our data, take 25% of it, hold it off for some later evaluation when I want to see how good I'm doing, and use the other 75% to actually compute some statistics. I'm taking my admission scores that I computed on a previous slide, converting that to NumPy. This is going to be my y hat. These are my predictions. My baseline is just the mean. So I compute my means, and then I compute np.full is my baseline. So these are my means. I want to see whether or not my y values for the test indices are above or below the baseline. This gives me the predicted values of y for the baseline. And then I can compute whether or not, what the mean squared error is between the actual values of y and the baseline. And I'll just basically plot it here, okay? So this is maybe getting a bit ahead of ourselves. So I'm going to park this for now. You should park this as well too. I think when we're going to go through eventually an introduction to modeling and making decisions, we can come back to this module later. But we haven't even really defined mean squared error yet, really fully yet. So we'll come back to this a bit later. How well do what does our rule look like? So we have one of our measures of input is our test score. So people write tests when they're applying to a university. They get a score. Some people got well below 40. Some people got nice and up to 100 or so. So that defines the x-axis. And then that was part of an overall decision-making process that got the admission score, which is on the range of 0 to 100. So this is the score we get from using our dot product, subtracting the bias b, and so on. Okay. Now, you look at this graph of test score versus admission score, and what pattern do you observe? There seems to be a bit of a upward trend, right? So people with low test scores tend to have low admission scores. People with high test scores tend to have high admission scores. There's a ceiling here that all these points kind of bump up against. But generally, this is a kind of a very mushy cloud of data. They don't fall in a line. You can't predict the admission score with only the test score alone. Imagine somebody scores a 70 on their test, right? Their admissions test. Well, that can translate to an admission score of about 45, or it can translate to an admission score of 100, right? Similarly, they can have a test score of about 50. This can also translate to admission score of about 45, or up to a admission score of about 90. Okay, so you cannot predict the final score we care about, the admission score in this case, only using one of our variables. In so many cases, the thing we're trying to predict, the one thing we're trying to predict, is going to be a combination of a bunch of different factors, and those different factors are going to be weighted in different ways. They're going to be more or less important than the others. How important are those factors? We set those ourselves, so we decided that the weighting factor for GPA should be 18, for example, and that was just given to us. But maybe that's a number that we want to fiddle with, and we want to maybe even learn it from data automatically. Okay, well, that's what machine learning really is, and that's where we're kind of pointing to with all of this work. So we'll get there soon enough. I'm going to talk about broadcasting briefly. This is a little bit of a stretch here, so just keep that in mind. Broadcasting is NumPy's rule for applying element-wise operation to arrays that might have different shapes. So we talked a little bit before about having two vectors. Maybe those vectors have different lengths, but you still want to combine them together in some way. So imagine y hat has shape n, nothing, so it's a vector of length n, and b is a scalar. So far, broadcasting is safe. You take, like NumPy, what it's going to do is take b, repeat it n times implicitly, and just add b, once for each of those elements of y hat. So it's going to basically add b n times. This is where the trap occurs. Imagine if you're trying to subtract a mean along like the incorrect axis. Okay, so you've computed mean on GPA and you're trying to subtract it from test score or vice versa. If you do that, like we talked about when we were talking about scaling, we're kind of centering the data in two ways. We're correctly subtracting each column's mean, but we're incorrectly doing that through this broadcasting step. We're subtracting the one mean value from all of the columns uniformly, which will change the meaning of the data. So here's the code that basically just describes what I'm saying. I compute like the mean of my features, mu. So I have the mean of GPA, test score, extracurriculars. And if I just subtract these three means from X, I will get X-centered, which, all of my GPA data will be shifted according to the mean for GPA. And all of the test score data will be shifted according to the mean mu for test scores. So it's all good. If I took the mean across the rows, so now for some reason I'm taking the mean of one student's GPA and their test score and their number of extracurriculars. So now I'm not taking the mean over the zero axis, over the rows. I'm taking the mean over the one axis, the columns. Now suddenly things just don't really make sense anymore. So now I have like my mu rows. I try to reshape them. I get, like, I basically swap things to this shape N1. This is one of those things I think you should look into yourself. So I'm asking you to run through lines 6 to 9, do these steps, and see like what happens as you're performing these steps. So keep on writing out X in mu rows and mu rows column as you go to get a sense as to what's actually being done in this code. But now we're just going to compare them a little bit. We're going to compare the GPA centered properly, because I've computed the means over like summed over all of the rows, which is what I'd like. That means the mean in my first dimension represents the mean of my first column, and so on. It makes sense, as opposed to taking the average over columns, which doesn't make sense. Now, go ahead and see what happens. Take the GPA score. Take the first element. Here I'm only looking at the first five rows here. So again, the first 5 rows, the first element to the fifth element is represented by :5 here and here. But yeah, I'm just taking the GPA centered properly. You get values like this. GPA centered incorrectly takes these means computed over columns, and now these values have no really meaning to us anymore. This is the kind of mistake you're likely to get if you're not really careful with regards to which dimension you're computing statistics over. So it's important. One thing you're doing, especially in these early days, is when you're computing these means and you're computing these subtractions or you're computing products, take the time and make sure that when you're performing these functions that the result is actually what you expect, and you can check that quickly by writing it out yourself and printing out the results to the screen like I've done here. So let's go back to the metrics choice. We've taken these measures, we've used this score, and the score is helping us rank applicants for review. We care about the quality and we care about error, right? We talked before about the error where you triage, you discard a good applicant, and the error when you admit an applicant for further evaluation, which maybe you shouldn't have. Okay, we've talked a little bit about MSE scores as a simple metric. So if their score should have been one thing, and it was close, that's an error, but it's not as big an error as if it was very different. Later on, we're going to talk about admissions and rejections. This is a binary classification task. It's a binary decision task. And because it's a binary decision task, it's a classification task, we can think about it in terms of other metrics, like precision and recall. So we'll talk about all of those in a future module. Again, ethics comes in. All of this hides ethical gaps. So we've treated this as sort of just a use case that makes sense. But what happens, like these measures we're using, right? Extracurriculars can be a proxy for resources. So the high school a student comes from could have had a ton of resources to support students. Therefore, the students coming from those wealthy high schools would naturally have higher extracurricular accounts than those coming from less well-resourced high schools. So suddenly now you're giving an advantage to a student just because they come from a highly resourced high school. Maybe it's also the case that some schools are just more strict than others. Maybe some private school inflates grades of its students to make their students look good. This is just a possible scenario. And again, you're giving a benefit to students that come from those schools that inflate grades, and maybe that reflects some underlying bias. Okay, so even in this simple toy example, we have several very obvious ways in which certain students will be advantaged over others. We talked about transparency. Transparency isn't exactly being neutral. Okay, just because we have all of the data available to us and we can provide all of our code and all of our decision making and all of these dot products to the committee that's making decisions, this doesn't mean that we're absolutely neutral and that these biases don't exist in our analysis. Okay, just because the source code is open doesn't mean we're neutral. So again, there's always ways to mitigate against these problems. Just because there are problems doesn't mean there aren't solutions to those problems. When you're actually in a situation, you're going to go ahead and document as much as you can. You're going to prioritize different aspects of these measurements for review. You'll run subgroup checks to make sure that you're not just like admitting everyone from this high school and rejecting everyone from that high school. You're making sure that the labels are collected in a way that makes sense and so on. It's very important. Quick check. Here is a handful of questions I'd like you to work on. These are going to be fairly easy and straightforward, but they'll help elicit any kind of challenges you're having with the material. So please go ahead and do that. Bring it to class, ask me questions, submit these along with your weekly activities, and I look forward to seeing you again next time.